Ladies and gentlemen, I'm going to start it. If you're listening, great. If not, good luck. All right, yesterday we talked about pH, and you calculated the pH and the pOH of a couple of things. And then we talked about the pH of strong acids and strong bases, and you knew if you knew the pH of the strong acid or the strong base, you also knew the concentration of the hydrogen ion or the OH ion, and you could take the negative log of that and find the pH or the pOH. And then we talked in depth about the pH of weak acids and bases, and we remembered that we were going to have to use a rice table to figure them out. We did a bunch of rice tables. So we did one weak acid, then we did a mixture of weak acids, and we recalled that the only thing that affects the hydrogen ion concentration in a mixture of weak acids is the strongest acid, and that is the one that has the largest Ka value. So we did that, and then we did the pH of a weak base here, the pH of a weak base here. So it's time today to go back and pick up with those things we did not do. And that would be the percent dissociation. Okay, does anybody even know what the formula for the percent dissociation is?
Yes, the other it's percent ions equals H plus over HA times 100%.
Okay, H plus over HA times 100%. And these would be the equilibrium concentrations, yeah?
Yep.
Would they? Okay, so this is what we're going to do today. And I did say to you, when you're talking about a weak acid or a weak base, concentration matters to the percent dissociation. Looking at these right now, 1 molar or 0.1 molar, which one do you think dissociates the most? A or B?
A.
B.
A. B.
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 B. All right, let's mathematically prove that. So HC to H3O2 will dissociate in an equilibrium expression to H plus C2 H3O2 minus. Agreed? Okay. This is a weak acid, so let's do our rice table. This will be A. Initially, we have 1 molar acetic acid, no hydrogen ions, and no acetate ions. The change is always like this. And at equilibrium, we have 1 minus X, X, and X. Ka for this is 1.8 times 10 to the negative 5th, and that's equal to X squared over 1. Remember that this is such a small amount that we can ignore that. So X is equal to something that I can't find right at this moment in time. What is it?
0.0042.
0.0042, and that is equal to the hydrogen ion concentration. And then the acid concentration at equilibrium would be H2C3O2 would be equal to 1 minus 0.0042, which is essentially equal to 1. All right, you have 3 sig fig here. It's going to get lost in the sig figs. So the percent dissociation is going to be equal to 0.0042 over 1 times 100%, which is equal to 0.42. Very little of it dissociates. Meanwhile, B. we have 0.1 molar. The Ka value is still the same. X is equal to 1,3, one more, sig fig 4. Okay, that's the hydrogen ion concentration, the concentration of the acid. The acid is 0.1 minus 0.00134, which is
0.0987.
We're going to call that point what?
0.0987.
Okay, we'll do it that way. So the percent dissociation is equal to 0.00134 over 0.0987 times 100, and that is equal to 1.3? Yeah. Okay. So it turns out that the less concentrated one dissociates the most. All right, moving on. Now let's do this kind of backwards. Lactic acid, HC3H5O3 is a waste product that accumulates in muscle tissue during exertion, leading to pain and a feeling of fatigue. In a 0.1 molar aqueous solution, lactic acid is 3.7% dissociated. Calculate the value of Ka for this acid. Well, lactic acid dissociates in this manner. And the Ka expression would be everyone with me?
Yes.
All right. We do know the lactic acid concentration, and that is 0.1 molar. The hydrogen ion concentration is 3.7% of 0.1. So that would be 3.7 over 100 times 0.1 is equal to 0.0037. Yes? Okay. So the percent dissociation is equal to 0.0037 over 0.1 times 100%. What am I doing? I don't know. I was doing some problem that wasn't asked for. It's asking for the Ka. Just going on autopilot. Okay. If 0.0037 is the concentration of H+, it's also the concentration of the lactate ion, yes? Because they're 1-to-1 stoic. Now, how about if we just pop it into this, 0.0037 times 0.0037 over 0.1, and that will magically give you this number. Okay.
And then when we're doing the, if we're trying to find Ka, did we say earlier to disregard water in our?
Yes. In any equilibrium expression, because it's a pure liquid, its concentration isn't going to change. All right. So that leads us to this giant problem. And this giant problem requires me to have another piece of paper and you to listen carefully. Okay, they want to know, okay, here we go. So phosphoric acid, and we're going to do a titration with phosphoric acid, and we're going to watch each one of these dissociations. So the first time, phosphoric acid in water loses a proton and forms H2PO4 minus 1. H2PO4 minus 1 also loses a proton to become HPO4 minus 2. And then HPO4 minus 2 loses its final to become the phosphate ion. Now, these are all weak acids, are they not? So we know the only thing that's influencing the pH here is this, the strongest acid. So we're going to use that to solve this mega problem. It would like to know the pH of the solution and the equilibrium concentrations of everything else in the solution. Now let's recall this is all happening. So the first thing, let's find the pH, and that would require us to look at the dissociation of phosphoric acid. So initial concentration is 5 molar phosphoric acid, none of this and none of this. The change to get to equilibrium is this, and at equilibrium these are the concentrations that we would have. The K for this is 7.5, the Ka is 7.5 times 10 to the negative third. That's equal to x squared over 5. Remember, I get to disregard that. X is equal to 0.193 molar. All right, let's figure this out. H3PO4 is 5 minus 0.193. H is 0.193. And H2PO4 minus 1 is 0.193. They ask for the pH, so the pH is equal to the negative log of the hydrogen ion concentration, and that is 0.72. So we have figured out 0.72 is the answer to this. The math here is 4.8. So at equilibrium, the concentration of the phosphoric acid is 4.8 molar. And that's all we know from this. Now, let's go ahead and figure out the next dissociation. H2PO4 minus 1 will dissociate into H plus HPO4 minus 2. The Ka value for this is 6.2 times 10 to the negative 8. The initial concentration of H2PO4 is what? 0.193 molar. The initial concentration of the hydrogen ion concentration is 0.193 molar. How much of this do we have? 0. The change that occurs at equilibrium to get to equilibrium is this. Everyone agree? All right, ladies and gentlemen, am I going to disregard this X? In the equilibrium expression? Yes, I am.
Okay.
Remember, I'm going to write 0.193 down there. Can I disregard this one then?
No.
Uh-huh.
Wait, what?
Wait, what?
I thought you really did.
Yes, you can.
But I thought you said...
In this calculation, if I'm saying oh, so little ionizes it doesn't matter on the bottom, on the top, so little ionized it doesn't matter. Uh-huh.
told us otherwise.
Get it? So these are going to cancel. And the HPO4 minus 2 concentration is 6.2 times 10 to the negative 8th molar. All right, that means that at equilibrium, H2PO4 concentration is equal to 0.193 minus our X, which is Really? 0.193 molar, isn't it? So now we have the answer to this part of the problem. The equilibrium concentration here is 0.193 molar. We're getting there.
Is this why we say it's like one hydrogen?
At a time. Yeah. Okay, moving on. Here's our last ionization, P4, HPO4 minus 2 will dissociate into this. Our initial concentrations are 6.2 times 10 to the negative 8. 0.193, very nice, and 0. The change that occurs is this. The K value for this is really teeny. It is 4.8 times 10 to the negative 13th. And that would be equal to this. I'm disregarding the x here. X is equal to the ridiculously small number, I don't even know, 1.6 times 10 to the negative 19th. All right. That means at equilibrium, the HPO4 concentration is 6.2 times 10 to the negative 8 minus x, which is 1.6 times 10 to the negative 19th, which is 6.2 times 10 to the negative 8. That is just negligible. The PO4 concentration, bad me. If you don't put charges on ions where they belong, everything is wrong. The PO4 minus 3 is equal to x, which is 1.6 times 10 to the negative 19th molar. That is the end of this problem. That is a mega problem, is it not? So, yeah, this is 6.2 times 10 to the negative 8 molar. And this is 1.6 times 10 to the negative 19th molar. All righty. Are you good to go?
If that's not on the plan.